Hi everyone. Today we're going to do chapter 4, recursion or recursion. Most of the time, people wonder what is recursion or what does it do in computer science. Recursion is a repetitive task of the program that we're doing. If we want to do a recursion, if we want to do a task that is repeating, recursion is doing. Most of the time, we use a recursion, which is a repetitive task. But firstly, we usually, I think we did in a previous, or if you've been programming before, when you do a while loop or for loop, when you repeat some taxes, they say you want to print four numbers in the list using for loop, and then you say this is what normally do. So there's another way to do, which is called recursive call. That's where recursive does. Recursion is a technique by which a function makes one or more calls to itself during execution, by which a data structure relies upon smaller instances of the very same types of structure in the representation. There are many examples of recursion in arts and nature. For example, the fractal patterns are natural recursive. A physical example of recursion used in art is the Russian Makrotoshiskap dolls. Each doll is either made of solid wood, or is hollow, or contain another Matryoshka doll inside it. In computing, recursion provides an elegant and a powerful alternative for performing repetitive tasks. In fact, a few programming languages such as Scheme, Smalltalk do not explicitly support looping contracts and instead rely directly on recursion to express repetitive repetition. Most modern programming languages support the functional recursion using the analytical mechanism that is used to support traditional forms of function calls. When one invocation of the function makes a recursive call, the invocation is suspended until the recursive call is complete. Recursion is an important technique in the study of data structure and algorithm we will see in upcoming chapters. We will begin with a few or four illustrative examples of the use of recursion, which is providing Python implementation for each. There's a function called factorial, or we create a factorial function, usually denoted as n with the exclamation mark. It's a classic mathematical function that is natural recursive definition. And then there is a ruler, a normal ruler at school. This is when you put at school. So there's those lines that attach a centimeter or repetitively. So you can do a recursive pattern that is expressive of a fractal structure. And then there's an algorithm called binary search. It's among the most important computer algorithms. It allows us to efficiently locate a desired value in a data set with up to billions of entries. And then there's a normal file system where you create a folder in your computer, and then you create a folder inside the computer so that you're repeating a task. File system for a computer is a recursive structure in which a directory can be nested arbitrarily deeply within the other directory. Recursively algorithms are widely used to explore and manage this file system. A factorial, you can say, okay, let's say 5 factorial. So in mathematics, 5 factorial is 5 times 4 times 3 times 2 times 1. It should give us 5 times 4, that's 20, 3 times 20, that's 60, 60 times 2, that's 120. Should give us 120. So this is a mathematical way of doing a factorial function or a factorial number, which is 5 exclamation H. So each time a number, let's say 5, and then each time a number is multiplied by a minus 1 number. So 5 minus 1 is 4. You multiply that number. 4 minus 1 is 3 until you reach it 1, because we don't multiply by 0, because any number multiplied by 0 is 0. And then a ruler I've explained the binary. When we search for a number in a list, the binary is always divided by 2 until you find the numbers. Either go to the left or go to the right. If the number, let's say there's a lower number and a higher number. If the number is higher than, if the number that we're looking for is higher, then it must go to the right side. If it's lower, go to the left side until you find a certain target. Factorial functions to demonstrate the mechanism of recursion. We begin with a simple mathematical example of a computing reveal of factorial function. The factorial of a positive integer n, denoted as n exclamation mark, is defined as the product of the integer from 1 to n. If n is equal to 0, and then by convention or by law of mathematics, that is equal to 1. More formally, if any integer n is greater than or equal to 0, and in factorial is equal to all from 1 to n, so n times n minus 1, n times n minus 2, etc., etc. For example, n 5 factorial is equal to 5 times 4 times 3 times 2 times 1 is equal to 120. The factorial function is important because it is known to equal the number of ways in which n distinct item can be arranged into a function that is the number of permutation of n items. In mathematics, for example, we're looking for a character, A, B, and C. We can arrange this number into 3 factorial. It means we can arrange the number in 6 ways. The 3 factorial is 3 times 2 times 1, which is 6. ABC, ACT, ACB, BAC, BCA, CAB, and CBA. A is a natural recursive definition for the factorial function series. Observe that 5 factorial is 5 into 4 times 3 times 2 times 1, which is 5 times factorial 4. More generally, the positive integer n we define as n factorial. This is a recursive definition, can be formalized as n factorial is equal to 1 into n. This definition is typical of many recursive functions. First, it contains one or more base cases which are defined non-recursive in terms of fixed quantity. In the case n is equal to 0, n is assigned to 0 is the base case. It also contains one or more recursive cases which are defined by appealing to the definition of a function being defined. The recursive implementation of the factorial function, recursion is not just a mathematical notation. We can use recursion to design a Python mathematical of a factorial function. When we talk about a base case, base is where we are told to stop, where you stop your program, because if it doesn't stop, it's going to go infinite. So it's going to go further until it crashes your computer. So if we run this code, we define the function which is factorial with the n. If n, this is a base. If n is equal to 0, you stop, you return 1. Or else you run this n times factorial n minus 1. It's going to say, let's say it's 5. N is 5. So we say 5 times factorial n minus 1. So 5 minus 1 is 4. You multiply this 5 by 4, which gives us 20. And then go again, is ask, okay, is n equal to 0? It says no. And then you come here. N times, so now it's 4. 4 times factorial is minus 3, which is 4 minus 3, which is 3. 3 times 20. 3 times 20, the one that we added there is 60. And then go again is n minus, so n now is 3. Is n minus, is n equal to 0? Says no. And then you come back. Is n now is 2. So we say 60 times 2 give us 120. And then you say minus again, say n now is 1. Say n minus, is n equal to 0? Say no. 120 times 1 is 120 minus 1, which is 0. Now n becomes 0. Is n equal to 0? Yes, and then stop. And then you print it. Let's see if we can try to code. Then I'm calling this this function vectorial. I'm giving, okay, let's give it 5 and see if it's gonna run. It does give us 120. So it run diff factorial. This is image is 5, and then 5 got to say no, and then it goes there. It keep on going back and back. That's why they say it's a recursive. So the recursive is a function that go to itself every time until it reaches the base, which is 0. A recursive implementation of a vectorial function, which we just did. Okay, that's where we run. This function does not use any exclusive loop. The follow-up while loop is just use that repetitive. Representation is provided by the represented recursive invocation of the function. There is no circularity in this definition because each time the function is invoked, the argument is smaller by 1, and when the base is reached, no further recursive calls are made. We illustrate the execution of a recursive function using the recursion trace. Recursion trace is where we trace out as our code works. This was each entry of the trace corresponds to a recursive call. Each new recursive function call is indicated by a downward arrow to a new invocation when the function recalls a return. An error showing this function is drawn and then a return value by indicated alongside this error. So you can from there, there's a factorial, it's 4. From here it goes there, the from here it goes there. From here up until it reaches the end. This is the recursion trace. Let's go step by step. A recursion trace closely mirrors the programming language's execution of the recursion. In Python, each time a function, recursive or otherwise, is called a structure known as the activation call or a frame. Every activation record or a frame is created to store information about the process of that invocation of the function. This activation record includes a namespace for storing the function call as parameter or local variable. Remember, we discussed in, I think, in the first chapter where we developed the namespace or the local variable namespace where you hold these are namespace. So every time you call, it creates a space for it. When the execution of a function leads to a nested function call, the execution of the former call is suspended, and its execution stores place in the source code, as with the flow of a control should continue upon the return of the nested call. The key point is that there is a different activation call for each active call. This is the one that we're talking about, the drawing a ruler. In the case of drawing a futura, there is also no compelling reason for preferring recursion over a direct iteration with a loop. There's more complex example of the use of recursion. Consider how to draw the marking of a ruler. Here they're drawing the ruler. This is from 1 to number. It's ruler 1A, ruler A, ruler B, and C. They all repeat. Go it again. So it's in order to have the same length, you must do exactly recalling. The three simple outputs of the English ruler drawing: A 2-inch ruler with a measure 6 of length 4, B at 1-inch ruler with a measure 6 of 5, C with a 3-inch ruler with a measure 6 of 3. A recursive approach to ruler drawing in English pattern is simply called a fractal. That is the shape that has a self-recursive structure at a various level of magnification. Consider the ruler with a measure 6 of length 5, shown in 4.2b, including the lines containing 0 and 1. Let us consider how this will reduce of the ticks lying between these lines. In general, the interval with the central tick length is L greater or equal to 1, composed of an interval with a central tick, a single tick, which is L, and the interval with a central tick of L minus 1. And that's where we throw the line, give the argument of tick length, label check. We declare the line with a dash. Then if the tick label plus if the tick label is added to empty space and then plus the tick label, you throw the line. You draw interval length space. If the tick is greater than 0, you throw the interval length minus 1. Throw the line length, you throw the interval length minus 1 until, and then you draw the ruler. That's where number of inches 3, measure length. You can say 0 or 1, and then you run this recursively until the ruler is done. This is throw interval. This is also a recursive trace where you check how does the trace goes from here. Here you draw the line, or you draw interval, draw the line, 2 lines through until you finish the ruler. Partial recursive trace of the draw the line. The second pairing of calls for a draw interval 2 is not shown. This is identical to the first one. And then come to binary search. In this section, we describe a classic recursive algorithm binary search that is used to efficiently put a target value with a sorted sequence of n elements. This is among the most important computer algorithm, and it is the reason that we so often store data in a sorted order. Our data is, the list is 16 index, but because we start from 0, so it's going to end at 50. Our data is under sorted list from 2, 4, 5, 7, 8, 9, 12, until 37. Value stored in sorted order within an indexable sequence such as Python list. Numbers are at the top are the indexes. When the sequence is unsorted, the standard approach to search for a target value is to use a loop examine every element until it should either finding the target or exhausting the data set. This is known as sequential search. So when you're looking for a number, let's say you're looking for 22, if it's not sorted, it's better to use normal or typical loops. We call it a sequential search. This algorithm is runs in a big notation O of n, which is linear function or linear term, since every element is inspected in the worst case. When a sequence is sorted in indexable, when a sequence is sorted and also indexable, there is such more efficient algorithm for intuition. Think on how you will accomplish this task by hand. For any index j, we know that all the values are stored at index 0 until the last index, which is j minus 1. Less than or equal to the value of let's j of j, which is let's say 16, the one that we put in top. So all the values stored at indexes j plus 1 until n minus 1 are greater than or equal to that at index j. This observation allows us to quickly reach at home on a search target or to quickly find the target. Using the variant of the children's name, high, low, we call an element of a sequence a candidate. If at current stage of the search, we cannot rule out the circuit, we cannot rule out that this item matches the target. The algorithm maintains two parameters, low and high, so that all the candidates entries have an index at least low or at least at most high. Initially, we initialize and to 0, high, and to -1, we then compare the target related to the median candidate. Median, which is the median or the half, the center target. So we say index is assigned to low plus high divided by 2 or half of it. So in these cases, we consider if the target equals the center. If the target is in the center that we're looking for, and then we find what we're looking for. If the target is less than the center, the data mean, then we start again, go back and do the recursive first half of the sequence, and that is the interval indexes from the lower on your left side to mid -1. So mid becomes the highmost, and then you minus it the one target. If the target is greater than the center, then we do a repetitive task on the second half, which means on your right side. That is on the interval of the indexes from the mid +1, and from the center, the mid is becoming lower until high to the last indexes. If it's unsuccessful, or if you couldn't find the supposedly target index or number, it means lower is bigger than high. It means that it ends. This is a binary search. You're giving the parameters. Usually, this parameter, this search is run on a big notation of big O of log of n with a base of 2, because computers run at binary digits. So we run this. We say diff binary define the function, and then if lower is greater than high, we return false, means we can't find. Or else we assign mid as lower plus high. So the high number this is low and this is high. So the mean we divide low, we add lower and high, and then we divide by 2. So we're looking, this is the mean. We assign this is the mean, and we add this lower plus and then divide by 2. And then we say if the target is equal to mean, if the target is here, let's 1, 2, 3, 4, 5. If the target is 3, and then you represent 2, because 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 the mid center of this list is 3. But or else if the target is less than mid, if the target is less than the center, and then you go back and do the recursive, you go back and progress. You say data, which this is the data, D for data, and then the target, the state, the target is 2, low is 1, and then mid minus 1, which means the mid become the higher now, high number, mid minus 1, it means this minus this. So this is 3, and then minus 1 is 2. If it's 2, and then it's return true, if we're looking for 2. If there is no, if the number looking for is 4, if the number that we're looking for is 4, and then this becomes false, so we go to the next if, or else return the data, target, mid, the mid become low, mid plus n, and then high becomes this. So the high now is the mid, the low is 3, and then the high is 5. So it's trying against check if this one is our sensor now is 4. So we're looking for 4. And then the algorithm runs. So because it's run like this, the runtime is notation of log based and it's a little bit efficient. Okay, yeah, that's where they explain. This is low, this is high, this is mid. We're looking for, if we're looking for 2, we find 2 here until we finish. It runs until we find this 22. In the file systems or modern or operating system file system directory, which are also sometimes called folders in a recursive way. Namely, a file system consists of top level directory, and then the content of this directory consists of the file and other sub directories, which in turn can contain files and other directories and so on. The operating system allows directories to be nested arbitrarily deep as long as there is enough space in your computer. Although there must be necessarily be some base directory that contain only files, not further subdirectory. The representation of this position, such as system, such as the file system is given here. This is the root, where this is a first folder. Within a folder, we have file course 16, course 252. Within there is grade, there is homework, there's program. Within here, there's project, grade. Here, and then this project in place until you reach the end of the file. Portion of the file system demonstrating a nested organization. Given the recursive nature of the file system representation, it shows not come at a surprise. It should not come at a surprise that many common behaviors of operating systems, such as copying directory or deleting directory, are implemented with the recursive algorithms. In this section, you consider one such algorithm computing the total space, total usage, disk usage for all the files and directories in a particular directory. So we run this got a space of 5,122K, 244. So it should run a system that will calculate the space from the space, and then you calculate how many, and then you do the total. commutative disks. So we use this. This is a algorithm space. You find a path. So you define a path here on top. A path is dash blah blah blah, and then you input how many codes, and then to check the size. And then if they represent a parameter, then you do the calculation, then return the total. We usually use, in Python, use the OS modular operating system, and then you use OS get size of the path, return the return the immediate its usage and the size, and then is it true? Is it the file exists? If it's true, otherwise it's false. Is it a list string that in the names of the string within it is initiated by the string path? If yes, yes it is. And then you join them together so that you can do the calculation. This is the implementation of the code. It's run this define the function which is disk usage, the path total OS dot path get the size of the path, and then does it exist? Yes. And then check each within the file until you calculate, sorry, until you find the last one, and then you add them together. And then from here you return the total. Recursion trace to produce a different form of recursion trace. We have included the extraneous print statement with our Python from the fragment code you did above, the one of finding the space. The precise format of that output intentionally mirrors outputs that is produced by the classic Unix or Linux entity. It reports the amount of disk space used by the directory and all content nested within. It can produce a verbose report as given in the figure. Here, the code that runs this is the total that is found on grid. This is the one that said on H1, HWH1 until this is the total of all. A report of this usage for the file system in figure 4.7 generated, which is give us all of it. Section 2, I think we have 2 minutes. Because I think I've done what the file system. Let me try and run fast. It's running what? What is it? Here, you can see we give a comment. This is what file system and recursive, and then we import the modular OS, which can take this, the program to run in within the system, and then we declare the path which is with the real code on my desktop on my computer, and then we define the function with the path. You remember the path is the one the path we're dealing with here. And then from there, you do a total OS that get the size. We check if the path exists, and then if it exists, then we create a file. You run a for loop file in OS direction on that path, and then you do the calculation, join them together. We do the join them together, and then we add. And then from there, you do the calculation, which runs, I don't know, 100,000, 180 billion of the file that I have, the strings on this folder. It's run calculated by each other. It's got 511, 600, and then it edits total of it, which gives this amount of number. And then when you're coming back, you're going to do the analysis of a recursive algorithm. As we did run on chapter 3 when we were doing the analysis algorithm, here we're going to also do some example as notation as a big O to summarize the relationship between the number of operations and the inputs of the program. In this section, we demonstrate how to perform these types of runtime analysis through recursive algorithm.